Hi everybody. Today we're going to continue our unit on solving quadratics, but we're going to put a little spin on today's lesson because what we're going to be looking at today are non-quadratic equations that can mimic quadratics. So what we're going to be doing is we're going to be looking at non-quadratic equations that are going to be solved using the same methods that we would use as if they were quadratics, all right? And we're going to look at a few different types of equations that mimic quadratics. So upon first inspection, you'll look at it and you'll be like, hey, that's not a quadratic. But a little bit closer inspection will show you that if we just change one small thing, we might be able to rewrite the equation in a form that's more familiar to us, okay? Let's just jump in right here and take a look at an example of a non-quadratic equation that kind of mimics a quadratic. For example, if we look at x to the fourth, right? X to the fourth can be thought of as x squared squared. And if we can rewrite x to the fourth as x squared squared, then we can treat the x squared as a quadratic term. So a simple substitution can do that for us. And we've talked about a way that we can do a substitution, a very common substitution that we do in algebra and higher level mathematics called the U substitution. So we're going to use U substitution today to rewrite our equations and turn them into quadratics, okay? So if x squared squared is the same thing as x to the fourth, then if we let u equal x squared, then the equation x to the fourth minus 9x squared plus 8 equals 0 could become u squared minus 9u plus 8 equals 0. All right? And then once it's written like this, we can solve it like it was any other quadratic. I just want to remind you of the different methods we've used. All of those different factoring methods for quadratics and completing the square and the quadratic formula. These are the ways that we solved quadratics in the past. The hierarchy, at least in my decision-making process about what method to use, is generally I start to see if it can be factored. All right, so if it can be factored, that's generally the approach I'll take first. If it can't be factored, then I jump in and I use the quadratic formula. And then in a pinch, if for some reason I can't use the quadratic formula, which generally I always can, then I'll go in and I'll complete the square. So let's get back to our equation. After we've done the U substitution, can it be factored? So in this case, this is one of those quadratics where a is equal to 1. So we're looking for factors of c that add up to b. And it does turn out that you can factor it as u minus 8 times u minus 1. And applying the zero product property gives us that u is equal to 8 and u is equal to 1. These are not the solutions, though. Don't forget that u is not what we're solving for. We're actually solving for x. So what we need to do is one last replacement of u back to x squared, and we get x squared equals 8 and x squared equals 1. Solving those for x will give us the square root of 8, which is plus or minus 2 square roots of 2, and then the square root of 1, which is plus or minus 1. This equation is a quartic, and so the maximum number of solutions, or zeros, that it can have is 4. And this one does have 4. It has positive 2 square roots of 2, negative square roots of 2, 2 square roots of 2, positive 1, and negative 1. So this is how we use a U substitution to turn something that's not quadratic into a quadratic. And then we can go ahead and solve it using the methods that we've learned in the past. We're going to take a look at a few more types of equations that mimic quadratics. Okay, we're going to use a U substitution for all of these, but you're going to see that once we turn them into quadratics, it's not that difficult. All right, so let's do another one. We're asked to find the x-intercepts. All right, so basically we're asked to find the zeros, right? Or find the solutions. So let's take a look. We've got x squared minus 1. the quantity squared, minus x squared minus 1, minus 2. Generally speaking, you can kind of see how we have something squared minus something minus 2. That something is what we want to call u. And I usually look in the middle of the expression or the equation to look at what I'm thinking u should be, okay? So I'm going to just let u, in this case, equal x squared minus 1. And then this equation becomes the quadratic u squared minus u minus 2. After I've replaced the expressions with u, I'm going to see if it can be factored. Are there any factors of -2 that add up to -1? Yes, there are. We get u minus 2, u plus 1. We're going to apply the zero product property here since we're finding the zeros. And that's going to leave us with u is equal to 2 and u is equal to -1. But we're not done. Remember, we're not solving just for u, we're solving for x. So since u is equal to x squared minus 1, we have x squared minus 1 equals 2, and x squared minus 1 equals -1. That's going to leave us with x squared equals 3, and x squared equals 0, right? We square root, we get x equals plus or minus the square root of 3. And then on this side, we get x squared equals 0. That's x equals plus or minus 0, technically. So there is kind of like two solutions built into one. We call that multiplicity of 2, because 0 actually is a solution twice. Remember, when you take the square root of something, you get plus or minus. And in this case, it's kind of strange because you get plus or minus 0, which is the same thing twice. So there are the solutions to this equation. If we continue on, we can look at a couple other different variations on this equation's reducible to quadratics. So if I had the equation x minus 3 square roots of x minus 4 equals 0, you'll notice, again, if you just look at it quickly, it's not a quadratic, but if you look a little bit deeper, you'll realize that the square root of x, if we square that, we get x, right? So x is actually the square root of x squared. Again, I like to look in the middle to see what I think u is going to be. So if I make u the square root of x, then u squared would just be x, right? This equation then would become u squared minus 3u minus 4 equals 0. Now, can we factor it? Yeah, we get u minus 4 times u plus 1 equals 0. That's going to mean u is equal to 4 and u is equal to -1. But u is the square root of x, so the square root of x is equal to 4, and the square root of x is equal to -1. Now, something interesting happens here, okay? When you're talking about radicals and square roots, right? I want you just to do a quick memorization thing here. Remember when we talked about our parent functions? One of our parent functions was the square root function. Do you remember what that looked like? Well, it started at 0, 0, and it kind of went like this, right? And we talked about the domain and range of the square root function. And one of the things we talked about was how the range was always positive. So the y values, or the output values of any square root, is always going to be positive. And we've gotten to the point now where we actually want to call this is called the principal square root, okay? So the positive square root is the principal square root. And so if you think about what we got for our two solutions, well, the last step before we got our two solutions, we got the square root of x is equal to 4, and the square root of x is equal to -1. But we know that the square root of something can't be negative, right? Because the graph tells us that the output, regardless of what the input is, the output, or the y value, can never be negative. So what ends up happening here is this whole piece of the solution doesn't add any solutions to our equation. And we call these extraneous, okay? Extraneous because in theory, they are solutions, but in reality, they are not. So be on the lookout for these. The square roots of something cannot be equal to negative, so they don't add any additional solutions to our problem, okay? But we still have one step to do on this other side here. The square root of x can be equal to 4, right? So how do we undo something that's squared? Well, square rooted, we square it, and we get that x is equal to 16. So there is actually only one solution to this problem. I just bear with me here for a second. Remember, this is the square root function, right? This is what the square root function looks like. And notice that it doesn't go negative, right? The output is never negative. I want to take a second and just, if I graphed that problem that we just worked on, you'll notice it kind of looks like this, right? Interesting, right? And we're looking for the zeros, or where it intersects the x-axis, and you'll notice it only does that in one location, and it's at x equals 16. So graphically speaking, we've just verified that there is really only one solution there. Okay, so we have one more to do, and this is with fractional exponents. I'm going to just change the color here for a second. Let's do purple. So remember that it's all based upon this exponent rule, right? The power to power rule. When we are raising a power to another power, we multiply the exponents together, and that's what happens when we are using a U substitution as well, okay? So for example, if we look in the middle here, we have t to the 1/5. T to the 1/5 squared would be t to the 2/5, right? Because 1/5 times 2 is 2/5. So t to the 1/5 is going to be our u, and if we square that, we get t to the 2/5. So u squared is going to be t to the 2/5. That makes this equation then u squared minus u minus 2 is equal to 0. What we're going to do now, can it be factored? Yes, we get u minus 2 times u plus 1 equals 0. That's going to mean u is equal to 2 and u is equal to negative 1, right? Yes, yes, yes. That's going to mean t to the 1/5 is equal to 2 and t to the 1/5 is equal to negative 1. Okay, so what do we do at this point? T to the 1/5. Now, that would be equivalent to the 5th root of t. The 5th root of t is equal to 2. And this would be the 5th root of t is equal to negative 1. Fractional exponents are nothing more than radicals. Nothing more than radicals. So the lesson we learned up here, right? The lesson we learned with radicals, or the radical functions not being equal to negative numbers, applies when we get down here as well. Okay? So if you look closely, we have this 5th root of t, a radical of t is equal to negative 1. And so this, again, would yield an extraneous solution for us. An extraneous solution. The other side, however, we can do. And so how do we deal with t, let's say t to the 1/5 or the 5th root of t? Well, we're going to raise it to the 5th power. Raising it to the 5th power will eliminate the 1/5 or the 5th root, and we're going to get t is equal to 2 to the 5th power, which is 32. So again, what we're doing here is we're rewriting these equations so that they appear to be quadratic using a U substitution. I used the factoring technique here because all of these could be factored. However, after a U substitution, not all of them will be factorable quadratics. You may have to use the quadratic formula. but that's okay. You've learned how to use that, and you know how to do it. One of the other things I want you to remember is that radicals in general cannot be equal to negative numbers. They give you extraneous solutions. So now that you've gone through and you've looked at a few examples here, why don't you go ahead and do some practice? Check out the practice key, see how you did. And then the exit slip is waiting for you at the end of class today. If you have any questions while you're working or watching the video or doing the exit slip, please don't hesitate to contact me. I can help you. I'm just waiting for people to contact me to answer questions. Have a good one, and I'll see you next time.